So expectation maximization algorithm can be seen in various ways. One way is to look at it as a method of improving or obtaining maximum likelihood estimates for mixtures of Gaussians. It can be seen as a method for dealing in maximum likelihood estimation with the missing variables. It can be seen as a very general optimization technique, and it can also be seen only as a sort of generalization of k-means. And this last view is like the least general, but we'll start with it because it's quite a simple notion, and everybody will remember that. So I will just switch to new share. I want to share this window, this one. And what we'll try to do now is to see, to look at okay, let me, okay, so you should see now, do you see an image of a Yellowstone National Park? No, it says screen sharing has been, no.
I see a line, a white line on a black background.
Yeah, so there's a problem with the sharing. Let me do that again. Your screen has been paused. Why? New share. Okay, let's try this. Can you see my screen now?
Yes.
Okay,
Yep.
fine. So I'll do it per screen. Doesn't matter, not per window. Okay, so we'll be talking about the Old Faithful data set. The Old Faithful erupts at difficult to predict times for difficult length, which is unclear, the relationship, but we have data like this about Old Faithful. One is telling us that the duration of an eruption, that's on the horizontal axis, and on the vertical we have time between eruption. You see there is some correlation, but maybe we can see this as clustering problem. We would like to cluster it into two. And last lecture we had about k-means, and with k-means we could start by some random initializations. We talked mainly about initialization with k-means plus plus, or with some random so the points here, these are not some points from the data set, but anyway, it will end up in some fairly reasonable solution, but maybe this part looks strange. And one way to look at this, you remember k-means, was that we had clusters, they were initialized, and every time in the iteration, each point was hard assigned to one cluster. And moving towards the EM algorithm, which is the core of this lecture, we'll now introduce k-means, soft k-means. So let's look at k-means once again, and this time through a slightly different formulation. So if you think about k-means, everything is coded, the state of the clustering algorithm is coded in this matrix R, where every row describes a point, and it says it defines the assignment of a point. So the first row is 1, 0, 0. It means that the first point is assigned to cluster number 1. The second row, 0, 0, 1, it says point number 2 is assigned to the third cluster. Every row has to sum to 1, and every element of this matrix is 0, 1. And this fully defines the state of the k-means clustering. And this is already a third way of formulating the k-means cost function. And this time, we are summing over every pair of points and clusters. So if you remember from the last lecture, we were summing over all points, and instead of sum here, we had minimum of this distance. So minimum over the available mu's. And this is the same thing, because if R and K is set to 1 for the cluster K, which is nearest to Xn, it will also, this sum will be sum of zeros and one element. And if it's the minimum element, it's the same thing. Yeah? So, but now already, if we write down the k-means cost function, which sort of looks for a programmer's perspective, not the way to compute it, because now from a single loop over all data points, we are now doing a loop over data and cluster. But it allows us this sort of brute force way at looking at the problem to think, okay, perhaps we could generalize this notion of the responsibility. We can say, well, maybe it doesn't have to be hard. Maybe it could be something like a probability or soft assignment. We still have this constraint that the sum of R and K is equal to 1. But instead of being 0 or 1, the R and K could be something between 0 and 1. And then it would really have the role of probability. And we could say, well, don't worry about the E step, M step, because we'll talk about the EM algorithm later. But you can just think about the update rule. When we are calculating k-means, we were doing a straightforward mean. So this sum here, R over N, is actually summing the number of points which are assigned to cluster K, and this is a weighted sum. So if the weights were 1, 0, this would, in classical k-means, this would be exactly the same thing as the standard formulation. But if now RKN is not 0, 1, and maybe if it was, imagine it's non-zero for any element, every point would be possibly belonging to a different cluster, then this is a weighted sum, and the influence of point X on the location of mu K is non-zero for every point. Okay, so we can skip this. And one more thing, which is new to us, still thinking about k-means algorithm, we were just thinking about minimization of distances and various types of distances. We started with the L2 squared Euclidean, then we went to L1, then we were talking about strings, then we were talking about Euclidean, not Euclidean squared, Euclidean, and we never spoke about probability. But if we look at isotropic Gaussian, the distance, so maybe I can start drawing some things. So if we look at isotropic Gaussian, so we have a center mu, and then we have some diagonal covariance matrix with some sigma squares here. This would be in a three-dimensional case, and zeros here. Then you can see that the distance to the point X squared. So now if this is in 2D, so this is distance squared, is proportional to the probability of the point belonging to a cluster, or the likelihood of observing X given a normal distribution with the mean mu and some sigma, okay, let's say covariance matrix sigma. Yeah? So now we see that the k-means could be connected to probabilistic arguments. And we can think, aha, yes? Okay, so maybe I will mute. Okay, so we'll see that minimization of the sum of distances is actually maximization of the log of likelihoods. Because if we have a data set of points x, and we'll have if we have a single Gaussian, fine. We know that the probability of observing the data set given mu and sigma is a product. If we take the log, it will be a sum of normals. But now we all know this. But now we have a linear mixture of Gaussians. So a point x can be generated with the probability defined by this formula. How to look at that probability? Imagine that someone first has a die with k sides, and he throws the die, and with probability pk, you will get the result k, which means now generate the data from distribution, normal distribution with the mu k and with the mean of mu k and covariance matrix sigma k. So this is the mixture. You have like first someone draws, selects, this might be mu1, this would be mu2 with different covariance matrix, and that could be mu3. And the generative model is first pick your normal, your cluster, then given the cluster, generate a sample from the normal distribution. And now, so one can interpret these pi's as probability for the k, and the normal is the conditional. And now we can see that maybe something slightly modified as the k-means algorithm can be seen as something that maximizes the likelihood of the data given the k normal distributions. Of course, we were in the k-means, we were doing everything all the time isotropically, Euclidean distance squared. So this would be fine, maximizing the likelihood. So what were we doing? When we maximize the sum over all points, so we had points from I1 to the size of the training set, and we were trying to minimize the sum to the minimum over possible k's, xi minus mu k, this thing squared. And if you look at this, this is like saying assign x, this is like assign x to k. And if we think about isotropic, we were doing isotropic Gaussians, what we were actually doing was finding some locally maximum likelihood estimate of the centers. We were not dealing with sigmas. It was as if we were thinking all the sigmas are one, and we were not dealing with scale at all, or it's like we knew the scale, but we were shifting the centers of the clusters. We never talked about Gaussians, but we could say, aha, by doing minimizing sum of squares, this is maximum likelihood estimate for an isotropic Gaussian with a scale of 1. Actually, this 1 doesn't matter. If we have sigma here, then everything will be the same because we just rescale the data, and minimization something with a constant k here doesn't make a difference. Okay, fine. So if we go back to this, so imagine you have three mixture of three Gaussians, and the density could look like this. So these are isocontours of density. I used to do orienteering, so I can nicely see the shape like of the hill. I'm not sure how good it's on average, how easy it is to see density, but it's like a ridge which is, say, S-shaped, or like with two bends with very flat maxima. So okay, well, maybe better visualization here. Okay. So let's generate a synthetic data set. We get generated point from the three clusters, but actually when we solved the problem, we of course lost the information where the data come from. So one can look at this clustering problem as, yes, there was some cluster assignment, the color defining the cluster it came from, but this was lost. This data is not available to us. And let's see what would happen if you do, if we did k-means, it would always assign the point to one class, but in a soft assignment, you see that some points, this will be a function of the distances, will have like fractional assignments. So this is here coded by color. We are lucky that RGB can be seen as primary colors, and every ratio of the three distances to cluster centers could be color coded. This is for the whole space. And okay, maybe the last thing I will deal with this, I will show from this presentation before we go into a more formal introduction to the EM algorithm, is that the difficult thing is that the left part of this equation is what we know we knew this from maximum likelihood. Okay, logarithm probability of observing the data with all the mixing parameters, pi's, which says which cluster is how likely, and then the mu's and sigmas for all of those clusters. And the difficulty here is that it's sum log sum. When we had a single Gaussian, we had a sum over all points, logarithm of the expression for the density of the normal distribution. That was an exponential function, so the log and exponential are inverse, they sort of cancel each other. But now we have log sum, and then we have the normal, and this cannot be simplified, and a more complicated technique is needed. The last thing I'll show is how this experiment looks like, how this clustering with soft assignment looks like. We start, and it's not that things are red or blue, but points which are equally distant to both of those current estimates of the cluster centers will have 50/50 probability. They are shown in all sorts of magenta, purplish colors. We are estimating now not only the center coordinates, but also covariance matrices. And after a while, we end up with this type of distribution where I would say this is a pretty reasonable result. And if you remember, unlike the hard clustering, we get some nice split between the red and blue. And as it happens here, almost no data is sort of 50/50. Like in this, unlike this is almost like a hard clustering, although we never postulated it. It could happen that there would be a point somewhere between the two clusters which would be 50/50 after this process. And I think this is all I want to show from this presentation. And now we'll go into our presentation of the EM from the perspective maybe of optimization. So as I said, it could be used for two problems, like with the mixture models with latent variables. Latent means that the observations are complete, but the model is formulated in a way that allows to look at it as if some data was lost. So the mixture models would be easy if we knew which of the component of the mixture generated the data point, but if we don't know it, it becomes much more difficult. Or we have here a situation that some data points were missing. So imagine that you are trying to do some estimate of parameters of some 5-dimensional variable, and here we have sort of x, maybe 1, 1, x2, 1, x3, 1, and so on. And we would have the full data. So this is the first dimension. And the classical thing, if there's a missing data or someone forgot to fill in something, you would just cut it out. But that's actually wasting some information. Plus, if this failure is also somehow correlated with the values here, you will get a biased result. So imagine these are some maybe levels of water levels in the river, and this means the station is flooded. So here we have these measurements were not flooded, but if we remove all the measurements where point number 3 will give us no measurement. We will get for bias distributions of the other variables because they will be very high when this one is flooded. And EM algorithm allows us to use data with missing values for maximum likelihood estimation. So I will not go through this, but we know we saw this in the lecture number 2. If we have a single Gaussian, we draw an n sample and a sample of size n. We know that the maximum likelihood estimate of the parameter mean is the average of the points we observed, and the maximum likelihood estimate of the variance is the average of the sum of squares. Okay. And one of the examples we'll deal with in this lecture is the example where we have 2 Gaussians, and the data we are observing are a mixture of these 2 Gaussians. Could you give me some natural example where, for instance, this type of modeling could happen? Could you give me some variable x where the distribution x is a mixture of 2 Gaussians? So just to make sure that you can hear me or see me or whatever, say something like "I don't know" in the chat. Oh.
I don't know.
Okay, good. So
I have an idea, if I may.
yes, yes.
For example, if x is height and 1 Gaussian is the distribution of height in population, for example, for women, and the other is the distribution of height in I don't know a basketball team.
Yeah, yes. Well, that's even more complicated. You went all the way right, Petře. It was all the way right. But a simple example is height of men and height of women. Yeah. So it's not. Let's say that the height of man is distributed around 180. We worked on this maybe with standard deviation, something like 10 centimeters, perhaps. And for women, it's about 170, something like that. So when you observe, so what you will observe at FEL. At FEL, you will have something like this for man, and maybe, okay, something, so with prior probability 90% and 10% of women. And what you observe together is a sum of these 2 things, which will look like something like that. I wanted to pick a green pen. So you will observe this is the this is px at FEL. Yeah, given FEL, say. And it's a mixture of smaller normal distribution of females and a larger one. Now the PA is the probability of women, pi b would be the probability of men. Of course, they have to go together, sum up to 1, so it's actually 1 parameter. These mu's are mean height of men and women, and we can, for instance, say that A and B is the same thing, or we could model it. So if someone wants to estimate all these parameters at FEL, the technique we'll describe today will be possible. And notice one interesting thing. Yeah, it is possible through EM to estimate all these things: mu women, mean of man, probability of woman, probability of men, which is 1 minus probability of women at FEL, and we have the sigma man, sigma women, and we did that without a single piece of annotated data. So the EM algorithm is doing something called unsupervised learning. You can do this by putting some sort of measuring device, maybe some laser like a plane, at the entrance of the university. It will be giving you xi, and you will get this set. And without anyone labeling anything, you can actually get the parameters of both men and women distribution, yeah, and their prior probability. So this is, so EM algorithm is a method of unsupervised learning. Like this is maybe a new term so far. And when we're talking about classifiers like SVM, AdaBoost, we're talking about supervised learning because the supervisor, someone had to give us for every observation. Someone had to give us the label, and then we could start learning. So all these methods were supervised learning methods. Now we have unsupervised learning, and in principle we can discover this without anyone telling us anything. And then today we'll look at an example of semi-supervised, and that's the situation where you get these two things together. So some part of your data is unsupervised, some is supervised, and together this is called semi-supervised. So we'll now show an example how EM works for maximum likelihood for this type of case, and then we'll explain why it works that way. So often I find it useful to look at the problem this way, that we first say how it works. So we have our data xk, and we have some initial estimates of mu A, mu B. So for these heights, we can have very interesting, estimates. Now, I said that men, for instance, are the average height in the Czech Republic is about 179 or 180, but perhaps I felt it could be higher because the population is slowly but surely getting taller. So maybe our result will be slightly higher, but it's a good estimate. So we have these estimates, and given the estimates, we are just calculating. You can think about this as a likelihood term, and if this is the prior of the class, you can look at it as like joint probability. So this is the probability if this was right, mu A and sigma A, that's the probability likelihood of observing xk. From if it was from class A, this BB is the likelihood of, it's actually the joint probability because this is the prior, this is the conditional, and to compute the posterior, we normalize. So now the QA plus QB is 1 because we have made sure that if you sum these two terms, so these are joint probabilities, and if we divide, we get posterior. So the EM algorithm will say something like this. Take the current estimates of all the variables defining the generation, the model that generates the data. Calculate the posterior probability for data point K to belong to A and B. Use these as like relevance vector, and when you update mu A and sigma A and pi A, use the point X weighted with this contribution, with this factor which says xk contributes to cluster K with a weight which is equal to the probability that it was generated from the cluster K given the current estimate. And unlike with the k-means, we could have done this, but we are estimating the probability of each class as the sum of the contributions, the posterior probabilities. Yeah. Okay, I think that this algorithm is like the only thing you don't know why this is good, whether it converges and so on, but to write such a generalization of k-means, it's very easy. Yeah. So in k-means, we might have asked whether VK or VB, VA or VB was bigger, larger, and we assigned 0, 1. And then we did 7 with 0, 1, but here it's now a soft assignment. Okay, so please write I understand or ask your question. So nobody's writing okay in the chat, which I think is so one. So I expect more questions or confirmations. Okay, good. So 3, 4 confirmation. Okay. Okay, so Jan Neumann writes, he kind of understands. So what is the unclear thing here?
I think I'm just going to have to look through it once again.
Okay, fine. So this, like, for instance, if something is exactly between the two clusters, in k-means we had to break the tie and assign it one way. And if something is exactly in between, it will have QB and QA will be the same. And we are saying, okay, with weight 50%, I'm contributing to the calculation of the center A, and with 50% to B. Okay, so this is an example of how this would work on a 2 Gaussian cluster example, and the result is at the bottom, which is reasonable. Now, we can show, and we'll show that the EM algorithm improves the it improves the lower bound on the likelihood and the log likelihood or negative log likelihood, and then we'll show that we somehow have some guarantees for the process that shows that we are improving the likelihood, but there will be no guarantee for finding the global optimum. And actually, this is an interesting example which you can look in textbooks, that even if in 1D you have data, say you have data generated from 2 normal distributions, that exactly the case we had before. It turns out that the maximum likelihood estimate does not exist, because a model that would create a very narrow, like Dirac-like impulse at one observation, and the rest would be somehow covered. The other another Gauss would cover all the other data. The likelihood of such data goes to infinity. So this is an interesting thing, a sort of a failure case of the maximum likelihood method, that there is no maximum likelihood estimate because there exists a model that is a wrong one, which goes to the likelihood of which goes to infinity. So it's quite surprising, actually, that often with reasonable initialization, as an example shown on the slide, you get a very good result using EM algorithm, which is a local maximum because the global maximum doesn't exist. So we do not go to all these global, these singular cases of a very narrow Gauss on any point will have likelihood going to infinity. And so it's sort of maybe what this tells us is that the maximum likelihood method has a problem for this class of models, which is another reason to be sort of careful about its use. Okay, so now we'll show another example of using the EM algorithm, and after we cover this, we'll check we'll check most of the the theory which explains why this algorithm works and whether it converges and properties of that process. So let's have a look at this example, which is a semi-supervised, it will be a semi-supervised learning example. So we know that we are making observations about cars and trucks, and the variable y is the length of the vehicle, and x is the class membership. So x could be only a car or a truck, and we know that what we are observing is a mixture of cars, and the probability of cars at the location we are observing is pi c. The probability of track is pi t. They together add to 1, and the length of a car is normally distributed around mu c, perhaps unknown, with sigma 1, and the lorries have a probably much higher mu t, and they have a larger standard deviation sigma t, which is 2. So this can be sort of simplified to some constant kappa c and a quadratic function. This sigma 1 ends up with 1/2 minus 1/2 the probability of observation y e to minus 1/2 y minus the mean of the car length, and because of this 2, this is 2 times 2 squared, so 1/8, and the probability is proportional to distance from the mean of the truck class. Now, in the example, we have used mean car length 5 meters, mean truck length 10 meters. So here you see the distribution, and for probability of cars 60% and tracks 40%, these will be the joint probabilities. These are joint. And if we saw the y distribution, it would be the sum of these red and green curves. Okay, when we get the data, we will not know the parameters of the example, and that's what we are trying to estimate. So how will we deal with this incomplete data? If it was all complete data, which means for every single observation y, we would have the class x, then the whole thing breaks down into 2 independent problems. Estimate the mean length of cars, estimate the mean length of trucks, and when you take the derivative with respect to the mean of cars, only the car part will stay. It's irrelevant what measurements you make about trucks, and you will get the answer that we already know, that the optimal the maximum likelihood estimate is the mean for the truck and car classes. Fine. Now it starts interesting. We are at this incomplete data. Why incomplete? Because for some data we don't know the class. You can think about the semi-supervised setting. We have some car estimates, some truck. So for some observations of vehicles, we know the class. So this is something like this. We have an automatic system which is able to measure lengths of passing vehicles. For some couple of times, some operator comes and he sort of provides the ground truth, but maybe majority of the data could be of unknown class. So the y's, which we don't know which class they belong to, will be denoted with a sort of marked with a blue dot, and the dot says truck or car. That's the blue dot. Now, the probability of observation of a certain length is the probability that a car will appear of that length or a car appears of that length. These 2 classes situations are disjoint, so the probability is the sum. And it means, and I guess this is obvious, clear, that the estimate of the car parameter, which is mu c now, the mean length of a car, is influenced by the measurements which are not labeled, because you want them also to be high, the probability of these measurements appearing, that you want them to have high likelihood. And of course, that likelihood can be increased by the car or the truck distribution explaining the data with unknown vehicle type. Let's look at this formally. So the likelihood of the data we have is, now the first part is the likelihood of the data for which we know that they were from the car class. That's as before. The second part of the likelihood is the likelihood of the data which were labeled the track. And for all the other endpoints, the likelihood of that observation is, okay, log likelihood. The log likelihood is the sum of the probability that y appears for the car class or that the y appears with the truck class. So somehow we don't know, but for which is responsible for which point, but we'll have to find the mu c and mu t so that this whole term is high. So also there is a good high likelihood of the on the data points yi with unknown class. Okay, so please, could you confirm this is understandable? Or I think you should understand 19 and 20, these two lines. It's not difficult. It's just saying the likelihood of the data is the likelihood of the data which are class C, the likelihood of the data from class T, and then the likelihood of the data which I don't have information about the class, but the likelihood of observing it is the sum of the two. It either comes from cars or trucks. Okay, fine, good. Now let's have a look how the optimality conditions look like. So we are trying to find some optimal condition. So the place where the logarithm of L, which is the log likelihood of the data, with respect to parameter, we'll start with mu c. Here it's a scalar, but if it was a vector, we will end up with gradients, and it will be like formula, it will look very similar. Fine. So this part with y is coming from track, they are independent of the likelihood of the track points, doesn't depend on the estimate of the mean. So the mean doesn't on the mean, so of the car class. So this disappeared. And so here we have a quadratic function, we have a linear function here. And now it's important. So how does the derivative of this mixture look like? So derivative of sum of derivatives, and now derivative of a logarithm. So that's the argument, 1 over the argument. Now we take the derivative of the inner function. So this part is not a function of mu c, so that doesn't appear, but here we have derivative of the exponential, so that's the exponential. Derivative of the inner function is this linear part. So now we see that to find the optimal, the optimal value of mu c, that's the value where the gradient is 0, depends on the function on the mu t as well. So, and if we look, maybe we can interpret these quantities. So in the nominator, we have actually the probability of a car given mu c mu t for that measurement and that measurement. These two are probabilities of car given measurement plus probability of truck given measurement. And if you put these two together, this is probability of yi. Because it can be either car or truck. So, and then maybe there are two steps here. So this is yi. And now, maybe the best thing, like I will just recall that if you have some probability like PAB and you divide it by PB, this is PA given B. And it doesn't matter that you have already conditions on mu c, mu t. So if you have PAB given UV divided by PB given UV, This is PA given BUV.
If you're writing on a paper, I'm seeing your face.
You are right. You are right. I will switch, and I was writing, and so this is P. Okay, that's it. Yeah. So what it says, this is a definition of conditional probability, assuming that PB is not 0. And it doesn't matter that if these probabilities are already conditioned on some U and V, which means that we know that the values, then it's just like saying, okay, now we condition on B as well. So all in all, this is the probability of car given the current estimate of mu C, mu T, and yi, which is sort of logical. That's the thing saying, well, if you look at 32, it says, we will want something like the mean. This first part, the solution of this part is put mu C as the mean of the observations. And this will be saying, okay, for the mixed points, we also want this to be 0, the mean, but the weight of the point is the probability of the car given the current estimates. So that, if you remember, we were making this we said, okay, we'll calculate the current a posteriori probability of the car, and we made it as we postulated it. And now we see that this comes from the condition for the derivative of the likelihood with respect to mu C to be 0. The quantity car given the measurement of with unknown class mu C mu T showed up. And now we'll do something which confused me when I was a student very often in numerical recipes, numerical methods, is that numerical recipes is a very good book about numerical methods, is you say, okay, for this box, which is a function of mu C to mu T, we'll understand mu C and mu T as constants. So we'll plug the current values and treat them as constants. Whereas in the outer part of the formula, mu C will be seen as variable. Yeah. So this you will look at this equation as 0. You want the derivative to be 0, and you will say, okay, I want this. So these are the lengths of observations for cars, which we know are for cars. And then we'll say plus sum. This will be some coefficient. If you remember, so this sum goes for I from 1 to the cars. This goes for the 1 to M for the unknown class vehicles, mu C, mu T. So this will be our Q of I, and times, and this will go times I mu C. So here, this thing is now a constant, and this equation is easy to solve. So we say, well, okay, let's hope we can find, we are looking for an optimal value for this. This equation must hold for mu C to be a local optimum. So, well, for a minute, we'll forget the mu C is also here. Use the current estimate of this Q, solve for that. This is easy. If you think about it, this is just a linear single equation. It's very easy to calculate the solution of that. This will give us mu C will go to mu C prime or whatever. We'll have another, and then we'll iterate. We'll recalculate this coefficient, and off we go. And of course, the question is, are we improving the solution? What guarantees we have? For mu T, it will be exactly the same thing. There will be some P truck for the current estimates, This will be seen as constant. This will be seen as mu t variable and will start running. So if you look where we got, so what did we do? Okay, let's maybe recap here. We said, okay, we have some missing data. We have this classical thing, for label data supervised, then 20 unsupervised. We said, well, we need some values of mu c and mu t, which will give us for which the derivative of the log likelihood of the complete from data will be 0, and the condition for that to be true looks like maybe this 36 and 37. Now, because p is a complex function of mu c and mu t, we cannot solve this. But if we think about the p's as for a minute to be constants, which they are not, but we look at them, then it's easy to get mu c, mu t, recalculate p, and that's it. So 38 and 39 are just, or maybe 39 and 40 are showing how to update mu c with these coefficients q, and that's it. So, okay, we have some algorithm which hopes that why there's hope that this will work? Because if this probability changes a little bit, very small, probably the solution will not change much. And sort of, if you look at it just first, like, let's have a look at it with common sense. One can think, okay, this could work. Now, so the whole procedure is this. For this example, initialize mu c, mu t. How would you initialize mu c, mu t? Question, what would be a reasonable initialization of mu c, mu t? Of mu c and mu t?
Average of the known?
Exactly, yes. Jakube, yes, correct, exactly. Average of the known, given with these two, of course, this will not stay the same, but probably we are near. Given the mu c, mu t, we will calculate this probability that, or we can look at it as some coefficient q, but also we can interpret it as probability that observation I belongs to class car or class truck. We recompute the mu c, mu t from according to these formulae for 41 and 42, which are nothing but weighted averages, where points or observations which are sure to belong to a given class will have weight 1, and then the sum of the weights is the c. This is sum of the ones for the c examples, and something less for the not unlabeled data points. By the way, so these two sums sum to m. So, but the m is sort of split between the two clusters. And this is the essence of the algorithm. Step 2 is called expectation, because we are somehow calculating the probability of a point belonging to a class, and then the m step is given mu c. This is the update given the q's for the maximum likelihood of mu c and mu t. Okay, so as a soft assignment, you can see that these we can see the q's as the soft assignment to classes. So that's the relation to k-means. And now maybe the comparison of the two. So it's quite small, yeah, the difference. If you look at it this way, you somehow have to initialize. With k-means, you have to initialize. In k-means, we the queues were either 0 or 1, 0 for car or 0 for truck, depending which mean we were closer to. Here we don't make this hard decision. We just compute this QZ of I, which will sum up for the two classes to 1. So the 1 is sort of split. We recompute according to 45, 46. That was the same, but now, unlike with k-means, Q for this object I is not 1 or 0. It could be something between 1 and 0, and that's it. Yeah. So you see the analogy is quite similar, although with EM we have a nice probabilistic interpretation, whereas in k-means we're just saying, okay, let's minimize the sum of square distances or some other distance, and we were not giving it a probabilistic interpretation. In some sense, it's quite similar to nearest neighbor classifier, which at the first look doesn't look as anything probabilistic, but then when we looked into it more carefully, you can give it a probabilistic interpretation. Okay, so how do our experiment work here? We chose to generate 50 points from the truck distribution, 50 points from the car distribution, and 1,000 points from the mix, so where we didn't know which is which. So let's see what happens if we estimate from different mu1, mu2. So probably the only interesting case that if we initialize with something close to 5, so if we take 50 examples of cars which are distributed around 5 with standard deviation, and this is actually an interesting question. So what if we take 50 points from the car distribution and initialize the algorithm with the average, what will be the statistical properties of the average? What is the expectation of the average? Of course, the average is a random variable because the 50 points were generated at random. But what statistical properties does the average of 50 observations have?
Its mean is 5 and its variance is 1.
Okay, so the variance, no, because the variance of an average, okay, the variance will be reduced by the square root of the number of points. Like, it's sort of obvious, no, that if you take repeatedly 50 points and you get the averages, they will be much less spread than the individual measurements. And it's not so difficult. You should actually be able to do that after statistics. It's easy to prove that the variance drops with n and the standard deviation by square root. So it will be, so the average of 50 points will have roughly standard deviation of 0.15. And so we'll be starting with very high probabilities, somewhere around 5. And the same thing will be true for the trucks. Their variance too will be reduced by square root of 50, so by 7. So it will be something about 0.3, something like that. So it's very likely we'll be initializing from 5, like very close to this point somewhere. And you see that the convergence to the correct minimum, 5 and 10, is will happen from most of the initialization points. There is some other local, there's another local minimum, which is the other, like if it swaps the car and truck. If you initialize almost the other way around, you can sort of fool the method, but this is very, like if you initialize with the average of the known classes, for the known data, it will not happen. Okay, so fine. So there's one more example that we have in the lecture. I will not spend that much time on it, but it shows that the EM could be used in completely different settings than a mixture of Gaussians. So imagine you are in this scenario where we are observing in the mountains the temperature and the snow cover, and both are sort of binary. So you just say, okay, low temperatures say below zero, high temperatures above zero, and snow has two levels: little snow, which is also under no snow, and a lot of snow. So now you know that your model T, like the probability of T is dependent on some scalars, A, B. So imagine something like, if you are doing this observation in some village in the mountains, you don't know what T and S, what's this is to expect, but maybe A and B is something like altitude and maybe the distance from the nearest lake or something like that. And you would like to know, like, find the depend on this parameters A and B of the model. So someone told you that the TNS for a village depends on some parameters like altitude and distance from a lake, but you do not know the parameters of the model. So for instance, one possibility is that the model is A, 5A, and 3B, for instance. Yeah? So for instance, if A is something like altitude, you are, or maybe which one is this? S1 is a lot of snow, S1 is likely, exactly. So if A, so it's 5 times A, so something which increases the probability, like likelihood of high snow cover. Now, if you want to figure out this A and B parameters, and we have all the complete observations, how often in that village you have low snow, low temperature, high temperature, a lot of snow. This one is low temperature, high snow, and high temperature, low snow. So these four, you should know by now how to estimate A and B. Can anyone help me? How would you estimate A and B? So what is the probability? What is the likelihood? Let's say what we are interested in. What is the likelihood of A and B? And we know that the observation, given the observation, N00, N10, N01, and N11. Any idea? Anyone? So you should know this, and it would appear in the test. So we have seen N00 times observation T0 and S0. The probability of that thing is A. The problem of one of that observation is to observe it N00 times. The probability is N00. Now, then we have this T0S1. That has probability 5A, and that happened N01, and so on. We can take the log of this to make it out. So this, you should be able to write down the likelihood of some parameters given the observation for this model, because it's not difficult. So this is the likelihood. The log likelihood will turn these exponents into products and the products into sum. So we have this likelihood. There is a constraint that 6A plus 4B equals 1. Where does that come from? Because A plus 5A, which is 6A, plus 3B and 4B, which is 4B, is That's the probability of all the possible events, so it must be 1, and we get some solution, we get a solution. A and B, from these two equations, you will end up with a solution. Now, it could happen that you would like to know this, to get these parameters A and B for a village where they do measure how often they have low and high temperatures. So after a season, they say, well, we had T0 days with low temperature, T1 days with high temperature, and S0 days with low snow, and S1 with high snow level. But you don't know how it's correlated. By the way, how it's dependent. But if so, for this village, you have only this T0, T1, S1, and S0. If you manage to estimate A and B, from that, you can actually go for probability of TS, yeah, because you know the A and B's. So here you see this, why this example might be realistic. So some village just measures high temperature, low temperature every day, low temperature, high temperature, and they just give you the summary statistics. They don't tell you what happened a given day. But once you recover A and B, you have the full model. You can fill in the table on the left. So let's say what we have available. The log likelihood of the data. So the probability of T0 is probability of T0 low snow, this is A, plus the probability T0 low temperature and high snow. So the probability of T0 is 6A, and when it appears T0 times, it's 6A to the power of T0, and the log is this. Now, what is the probability of T1? That's 4B, because it's either this one or that one, and we end up with this type of formula, which says, okay, this is the likelihood of the data I have: T0, T1, S0, S1, and still A and B has to 6A plus 4B has to has to be 1, because that's the total probability of something. That's the probability of all events that can happen, which are disjoint. We are talking about elementary events. Fine. So now, if we take the derivative with respect to A and B to get the values for this village, we'll get two equations with two unknowns. And in the end, it's not so easy to solve, but we can solve this as it happens. This is solvable without EM algorithm, but let's solve it with EM algorithm. Make an initial estimate of A and B. Given this estimate of A and B, we'll be asking the probability for the missing data. So the observation will be like the missing data for the snow report. And we can, once we have an estimate of A and B, we can calculate the probability of low and high temperature for that snow level. And these are the formulae. These quotients, these quotients Q, they add up to 1. And now once we have QT, so we have the QT1, like the probability of T0, T1, we can do an update on A and B, which is here, and we iterate and we reach some result. So maybe this example is quite complex, but the point is that EM is not for mixture of Gaussians or mixture models. It can be used in any scenario where some data is missing. And here we knew only like S and the snow and temperature record. So we were sort of modeling it, saying snow is known, but for the given snow, we didn't know the temperature. And from that, we could get A and B. And these are the iteration formula. And now we have the question, does it converge and does it, are we sure to at least reach some local optimum? Why does this algorithm work? And now, so the last part of this lecture is like, let's say the theory of EM algorithm. So we were getting, what was the setup? We had a training set and we had, like always all observed values would be called O, and Z would be the unobserved variables, these which were lost. So, and our goal is to find the maximum likelihood parameters theta that are maximizing the likelihood of the observation. 64 is nothing more than maximum likelihood principle. Now, if we knew the missing data, which we don't have, then solving 65 would be easy. Think about maybe the Gaussian mixture. That would be saying, for every point, I know which Gaussian it belongs to, so this would split into separate estimates of maximum likelihood parameters of each cluster, but through this missing Z, everything is coupled. And what we'll try to do is to somehow deal with 64 in a way that resembles 65, where we are sort of trying to figure out what this Z could be and iterate. So let's assume that we have this so this is our observation, and we are trying to use the probability of Z, like the Z is the missing data, but what we'll do, we'll formally introduce here the probability of Z. You see, we just multiplied by 1, so we haven't done anything, but now we'll use the inconvenience of maximizing this thing is actually a logarithm sum of logarithm. So what we are trying to do is to do it as logarithm of a double sum. So we'll say, okay, it's a logarithm of sum. We will try to get it into sum of logarithms. Actually, this will be a convex combination because the QZ are all positive and they sum up to 1. So we will make an observation that logarithm, which is a concave function. So if we have a function, so we have a logarithm, which here it would be 1 and 0. So if you are making a convex combination of two values, so convex combination is like any point on a line segment between the 2 points, and that will be below. So if we have here x1, x2, and this point x is alpha 1 times x1 plus 1 minus alpha x2, and let's say that alpha is between 0 and 1. If it's 0 or 1, it will be the extreme point. So this is the point here. And then logarithm of this at this point x will be, you can see it, but it's provable quite easily. The logarithm at that point. So what is the logarithm at this point? This is log ln x, yeah? So maybe I will put this x in a circle. Yeah, this is here. And this will be more, this is more than linear combination alpha 1 ln at x1 plus 1 minus alpha 1 at x2. So this bit is just like a equation of this line. So that's what we get here. And it's less than the logarithm. Yeah. And this is because this is called the Janssen inequality. And we can say the way we have it here, I think it's the other way around. So this logarithm, this is the, yes, exactly. This is the logarithm of the, so maybe I would generalize this. This is a logarithm of a convex combination qi is more than a convex combination of logarithms at xi. And so it means that we will be able to, if we are able to deal with the maximization of this quantity, we will increase the upper bound of what we want. And that's okay. Probably the quantity here, which is the like, let's call it calligraphic L, is the sum of, these are like, this thing is like the probability of the observation given the current probability of Z. And if we look at all of this, the difference between our, like the lower bound and the true quantity we are trying to maximize can be expressed as formula 75, which can be seen as which is Kullback-Leibler divergence. So Kullback-Leibler divergence of two distributions. So let's say we have a distribution Q and distribution P. So distributions are something like, something like this. We are in a discrete case. At the moment, something sums for 1, and Qi and Pi are greater or equal 0. So these are distributions. And so maybe something like one would be like this, another one could look like perhaps like that. And Kullback-Leibler distance is one way of defining, so you can have many different distance functions of P and Q. For instance, you can say, well, I can measure surely an L2 distance between P and Q. But the Kullback-Leibler divergence, which is called DKL, it's not a distance because it's not symmetric. That's why it has this weird notation, which is sum over, and I will write it this way, Q log log Q over P. And this is the same thing with minus here. This is the same thing as sum Q log Q minus maybe something like this, Q log P. So what does it say? This is the entropy of the Q distribution. And you can think about, and this is always non-negative. Now, what does it say? Why is this a reasonable way of measuring distance between two distributions? You are saying, okay, the difference, I actually measure the difference between log P and log Q for different i's. I put here I, and I do it weighted by Q. Now, what does this mean? So if you have some discrete set of Q's, this is entropy and you can think about it, Q is the optimal coding length. So if you have symbols from some alphabet with probably generated with QI, the best is log QI is to the length of the coding word. Now, here it's the length. This is the coding length. If you code symbols from Q generated with probability Q, coded with length P. So this is longer, and therefore this is always greater than 0. And maybe it's not so important to know why this is called that way. The important thing is that we are trying to it can be shown that the expectation maximization algorithm tries in the 2 steps. It tries to maximize the lower bound and then minimize the gap. So both steps are improving the log likelihood of the observation. Now it's much more difficult than to prove this than we were able to prove, for instance, in k-means that the sum of distances drops for every step. Here it's more difficult, but the algorithm can be now seen as start with some initialization, maximize the lower bound, and then update the distribution Q. I will probably leave this. I think it's very difficult to get anything without like sitting carefully and reading this on your own. Maybe we can connect this algorithm with the car example, where you see what these probabilities are. So the the current parameters are the mu c, mu t. The observation are the lengths. The z variable, this is the unobserved, is the car. These were the Q2, the QTs. Now this is the discrepancy between the Qs, the current estimate of the Qs and the conditional one. So if these happen to be the same, the gap will be 0. And the good thing is that both of these steps that we are performing have they have a easy solution. So summary. EM is most known as an application of estimating Gaussian mixtures for really large dimensions. You can think about it that the M step computes probabilities that a given point is generated by a given component. The E step computes the unknown parameters effectively, like with these weights. And EM can be used for a much broader class of distributions than just Gaussians. Exponential family are those which have some sort of exponential family is sort of like proportional to x to something, and e to x to some other. This type of distribution. It's an iterative method and typically will not finish in a global optimum, besides some special cases. And as like with k-means, we need to have a good method of initialization. If we are in the semi-supervised setting, the observations on the classes is the natural way to initialize. If we are in a completely unsupervised setting, so we have just data, it might be quite tricky. And and I think that's it. I guess that this theoretical part, which shows what is going on, is something that cannot be understood during the lecture. It's much better to go through it after the lecture. You should be able to understand these simple examples, the two examples, and you should now understand the connection with k-means. So I think that the EM algorithm, understanding the EM algorithm, is one of the formally most difficult parts of the machine learning and pattern recognition course. So before the exam, it's necessary to go through this again and look at the, let's say, the underpinning of the method. Okay. Questions? We have like 1 minute.
Yeah, I have one question.
Yeah.
Can you go to slide number 11?
Yes.
Here, when we are taking the derivative of the likelihood with respect to mu c,
Yes.
I don't understand how did we end up with that numerator, maybe because I feel
Okay,
something
okay.
is missing. Like if you take the derivative of kc exponential part, so it will be itself, and then within the exponential part, it's minus half into 2 to the power into 2 because the 2
Yeah.
comes down, yi minus mu c, and then you go within this bracket and yi is constant, so it's 0, and I feel minus mu c should also be there in multiplication.
Wait. So, okay. So, yes. So we start with sum. Okay. We start with a sum of log of something, u. So we will end up with sum of 1 over u. That's clear, yeah?
Yeah.
Fine. Then inside that logarithm, we have x and some
Yeah.
expression. So the derivative of x is
X.
that's here.
Yeah.
And now we are ending up with yi minus mu c squared, yeah?
Yeah.
So the derivative of that is minus I minus mu c 2 times. That will cancel. That
The
will,
half.
yeah.
Yeah, and the mu c also, right?
And the mu c, so that will change the sign.
Okay.
But there's also this. Okay, there's this minus here because in the exponent, yeah.
Yeah.
So the two signs will cancel out, and we are positive.
Okay.
Yes,
Alright.
one minus is here, minus 1/2 in the
Yeah.
x, and one minus is from the minus mu c.
Yeah. Okay.
So it's fine, yeah?
Yeah. And one more question. Do you have any idea about the examination date for this subject?
No, this is important. To simplify things, so everybody will sit the written exam at 1 day. And to me, the best, I can set this date right now. Let's set it now in real time. So the examination period, can you see my screen? You probably can see
Yes.
that.
Yes.
So I usually like to do this fairly early in the examination period, but not too early, because if you have things like final credits and finishing your work, so what about something like Wednesday the 20th? This is the middle of the second week. It could be also Tuesday 19th. Maybe Tuesday 19th is better.
Sounds pretty good.
So I
Yeah,
will put it
sounds
here.
good.
On Monday I will, and now it will work like this. Okay, so this is the Czech abbreviation, don't worry about it. You will set it, you will do it with the checks. Everybody will do this written at the same time. And then the oral will be on the 20th or 21st. Depending, because it's like 22 of you, 20 plus 60. So I will, okay, on the 19th, I will announce who will be, on the 18th, we will correct the exam paper, and the oral, which is fairly short, will happen on the 19th or 21st. Yeah.
And it should be in school, right? Not online.
It's not a big deal, but if possible, okay. COVID permitting, it will be at Karlovo náměstí.
Okay.
If it does not permit, I will do it with
thank
you remotely like we are talking now.
Yeah, thank you.
Okay, well, I should have switched.
One question to that. For example, when we go home, I'm an Erasmus student, so when I go home for Christmas and I will come back in the next year, and I don't know the restrictions then, and maybe I'm in quarantine or something like that because I just arrived. What will happen then?
I'm a reasonable person, so if it's not possible, you will do this somehow remotely with the camera on. I've done it with a Swedish girl last year, no problem. So the simple plan is that we'll have one big written thing on the 19th, possibly in 4 or 5 rooms. Yeah, and the plan is to do it on the 19th. I will just phone the lady who is organizing this and ask her, and if not, we'll have to do some sort of like massive online test. Yeah.
Okay, thank you.
And of course,
Okay, that makes sense.
One more thing, when I'm saying this 20 and 21, you will, well, I'm not sure what is, I want to copy this and I'm not sure why it's not doing something. I want to copy and put it here. Yeah, so each of you will need only like 15 minutes somewhere in these 2 days. Yeah, so the written part will be done by everyone, and the oral is like each of you individually, but only 10 minutes or something like that. It's just checking that you okay. By the way, I forgot to stop the recording, so maybe I didn't stop the recording. I stopped the screen sharing. Hold on a second. Stop.